So what I wanted to today is do a recap on the stuff with position and momentum spaces or transformation. Okay, so just because again, it's one of these things where I just believe it's explained too carelessly and it's just difficult to understand from first principles. If I try to recap what I discovered last time, or the way that I was kind of the way that I found a good connection to is basically saying, hey, you know what actually we should do with GPT chat. I did ask this. I did ask the chat about these, and it actually told me. Continue with Google. It actually told me the thing with the Fourier transform. I want to ask why then, for example, right? Done. So, how do you transform from position space to momentum space? It's almost like. So to transform from position space to momentum space, you can use the Fourier transform. It's cool. It's a mathematical operation that can be useful in many applications, quantum mechanics and signal processing. To perform the Fourier transform, you'll need a specific formula. It depends on the type of function you're transforming. There are many results available. That's cool, but why a Fourier transform? Let's see what what it answers. Because it provides a convenient way to present the function in the different bases. In position space, the function is typically represented as a function of position, fx. However, in momentum space, the same function is represented as a function of momentum, such as fp. The Fourier transform allows us to easily switch between these. I understand, but I am not sure I understand why specifically the Fourier transform. It's funny because it's funny that it even doesn't, that even this thing doesn't kind of tell you, or it gives you like a meaningful answer, right? What I got to was basically, if I remember well, because momentum is proportional to the was it to the amplitude or to the, I think it was wave function momentum proportional to amplitude. Was it the amplitude? I think it was the energy. So momentum of a wave function. Not the momentum operator, computer momentum of a wave function. That's not what I'm looking for. Oh, it was the expected value. Yeah, something like this. This form, I'm sure I'll deal with it. It's because what it's hard about all these is it's just hard to keep sort of meaningful definitions of all these concepts, or definitions that, like, because they're a bit more abstract, right, than just say classical mechanics. So what am I looking for? I'm looking for momentums and wave functions. I'm looking for, there was something that I found a place where it said basically the momentum is the wavelength. No. The momentum is inversely proportional to the wavelength. Wavelength. Exactly. Momentum. Exactly. That's what I meant. The wavelength. It's inversely proportional. So in a way, it's like the more compact the wave it is, the more momentum it has. That is the broad, however this is pronounced, hypothesis. Exactly. So, and this is in a way, like, knowing these kind of makes it a bit easier, makes it a bit like, well, it kind of makes sense that then the Fourier transform kind of works, because you want to go to that frequency, to the frequency domain, because the wavelength is then proportional to the frequency, right? Yeah, oh, they're inversely proportional to each other, of course. It's kind of the same. So so you want to go to the frequency domain to basically get that is in a way, you know, that's why these two things kind of make sense, or it's not that makes sense, but it explains, it's intuitively understandable this way. But because the wavelength, sort of what is a wave, the wave function? The wave function is something that when squared, when you square it, it tells you, sort of, it gives you a probability distribution. It tells you the probability of finding a particle in a specific point in space, right? And it's sort of, if we just think about one-dimensional space, that is just that that x-axis. A momentum wave function would tell you basically if you squared it, would tell you what is the momentum of the particle. Yeah, what is the what are the probabilities of the, you know, what is the probability distribution of measuring a certain momentum. So because if you think classically, how would you, this is what I was trying to think about first principles. How would you go from one to another, right? So if you know the position, you cannot know the momentum, right? So, but if you have a series of, or sort of a function of what the position is over time, then you can calculate the momentum you can calculate the momentum essentially, right? Because momentum is then mass times velocity. So you can calculate the velocity if you know how position is changing. So from a wave function perspective, it's funny that it's kind of funny that it is possible to just switch from one representation to the other without having the time, the time component of it. You know what I mean? Like, this is just an example of a wave function, and it's time independent. It's just very interesting. To me, it's a bit confusing, right? It's very interesting. You can actually come up with, you can actually transform this to the momentum without knowing without really knowing how the how is that position changing. This is what kind of bothers me in actually right now a lot. Where is my thinking going wrong here? Should maybe get too fixed in with the formula of the Fourier transform, but there is an integral, so but it just yeah. It is kind of in a way fine, right? Because this is basically like saying, you know, what is the sort of what was that? Man, I should be able to use Replit for this. A bit of a plot Python plot of plot a function, right? Sine wave. Oh, actually, why am I even Googling that? You know what? We can just go ahead and try. Let's see. I think I have Replit open here, so we can open it up, and then basically, because I'm kind of working on this quantum Python kitchen sink thing. You know, as a template. But what I want to do probably is I want to go to my REPLs and just have like a quantum mechanic exercise. So just go to this one, right? Because essentially what I want to do is a normalization test, playground, and I have Ghostwriter. So how can I enable Ghostwriter, or how can I use Ghostwriter? Can I just say plot can I just say that? How to use, how can I prompt Ghostwriter? How to prompt Ghostwriter in Replit. It's activated already for sure. Complete code, explain code, perform, generate code. Generate code. So, okay, right click, generate code. I have to prompt it like this. Okay. Okay, generate code, Alt G. Okay, so plot the sine of x function. Let's see. It's cool because you don't have to think about any of this stuff. And that's just like, yeah. This is it's just fucking plumbing, man. So essentially the what I'm saying is basically what I'm trying to say is, so it makes sense that it's an integral, right? So this is just a great combination of tools. As like, what is the formula of the Fourier transform? It's thinking. I'm gonna break the chat block. Hasn't it shown the? Hasn't it just? Why it's not showing? Plot x y. Well. I thought that would. Should I have the output? I think here probably. Console. Oh, sorry. It runs because it runs the main program. I'm stupid. So what I should just write this in main. I should just write this in main. Can I show figure? Matplotlib is currently using which is a non-GUID backend. So which is specific from the common for which is given by the following formula. So is different from the function fx and automatic specifiers with a symbol representation. What is used? Is a type of integral transform. An integral transform is a mathematical operation that takes a function and returns a new function by applying an integral operator. In the case of the Fourier transform, the integral operator is defined by the formulation above, and it maps the function from position in space. Yeah, that kind of doesn't really tell me. An unrelated question. I am trying to plot something using Matplotlib, and I get this error. No, that's not an error. That's not what I'm getting. I'm getting this error. Look at this. It is. Can you specify back in you want, for example, back in before I go before. So in order to, because this works right out of the box in Jupyter Notebooks, right? So in order to show figures in Matplotlib, you don't need a figure. You can use functions by the backend. For example, tk-ag. Let's see. Generate code. The thing is, I don't have it there. Okay. I'd love to ask Ghostwriter some questions as well, but let's see if that works. Oh, sorry. I guess. Do I have to? I don't know if that's. Can I just? Yeah, it's probably redundant, but who cares? Yeah, I like that because it actually saves you the googling. See if that actually is going to show something in the output. Look at these, that's nice. Yeah, okay, cool. I mean, the thing is, if I Fourier transform, so plot a full transform of sine. Can you even do that? I don't think that's plotting the Fourier transform of sine of x, is it? Isn't it exactly the same? I think it's the same code. Is it? Isn't it? Yeah, it's kind of the same code. Can you just generate again? It's kind of the same thing. Anyway, I mean, how am I going to plot it, right? So it's not that I can plot it because it's just, well, it's another function. But anyway, what I was trying to get at is basically where am I trying? What I was trying to do? I was trying to understand. Yeah. So how is it possible to have a wave function? How is it possible that you can calculate the momentum wave function if you don't really have? Because in classical mechanics you have the you really need to have more information. It's like how is position evolving so that you can understand the momentum, right? If you know a position, then you really can't not know the momentum unless you know the velocity or something like this, right? So, and to know the velocity, you need to know, yeah. How do we solve this? So essentially, how do you even derive that, right? So you have a wave, it probably should, it just takes me back to the Wikipedia, momentum and position space. Because it's telling me the momentum representation of a wave function is very close to the transform in constant frequency domain. It was written right there. It's like, since the quantum mechanical particle has the frequency proportional to the momentum, describing the particle as the sum of its momentum components is equivalent to describing it as the sum of frequency components. So the Fourier transform. This becomes clear when we ask ourselves how we can transform one representation to another. So functions, okay, so suppose we have a three-dimensional wave function in position space. So you can, and I know I've gone through this like 10,000 times, right? So we can write these functions as a weighted sum of an orthonormal basis of orthogonal basis functions psi j r. Yes, and this is just the basis, right? Like that's kind of, it's the whatever the position space, right? Or in the continuous case, I mean, that's how you get the integral. Okay, so so you're saying this function psi of r is essentially, what you're saying is a of an integral. So you have psi k. So it's clear that if we specify a set of functions psi k, say that the set of eigenfunctions of, as the set of eigenfunctions of the momentum operator. the function so the momentum operator, and this is why. This is probably why you can do this, right? Because the momentum operator is where you have the differential of position. Essentially, the momentum operator, this is where you have the differential. So that encapsulates that calculation. So you're saying in a way you're aren't you saying that if you apply the momentum operator in position space, that gives you the momentum, right? So, but why are we now using these as bases? We're constructing it. This function holds all the information necessary to reconstruct that and is therefore an alternative description of the state. So in quantum mechanics, the momentum operator is given by these. The eigenfunctions of this momentum operator are these ones. And these are the eigenvalues. That's something else to look at. So essentially, and we see that the momentum operator is related to the position representation by a Fourier transform. I mean, this is just makes sense, as in it's just an outcome, right? Like, okay, so these I understand, so because you're using these, but I'm not sure why is this derivation saying I have these and I'm gonna express it as the sum of some kind of basis times a coefficient, right? Yes, that's fine. But then what is the basis that I'm picking? Why can I choose whatever basis? I'm choosing what am I choosing? I'm choosing a basis which is the momentum operator basis. And why am I doing that? Why am I doing that? So this is then the wave function in momentum space. And the other way around, it's just saying conversely wave function momentum space, right? It can be expressed as a weighted sum of orthogonal bases, and then we say, well, if the position operator is basically the delta, not delta, sort of the differential of momentum. I'm stuck at like why can we assume that if I'm using these bases, what I get here is the wave function of position? What is the meaning of the eigenfunctions of the momentum operator? Okay, so that's a good question. What is the meaning of the eigenfunctions of momentum operator? So a momentum operator is an operator that tells you that if you apply it to a wave function, then it will give you the momentum. So the eigenfunctions of the momentum operator are basically, those are these wave functions that will basically, the momentum operator will just scale them. So you know what I mean? Like this is where I'm currently struggling a little bit. Can I see here how long has the recording been running? Not much, right? Oh yeah, here, 30 minutes. So why can I just assume that that's psi of r? I understand, I'm following the concept. I can pick bases, but why is that true, right? That you can write it as this integral. The position operator what does GPT so what is the meaning of the eigenfunctions of the position operator? Okay, so well, yeah, they represent possible positions. Okay, yeah, that kind of, okay. Yeah. Okay, that makes sense. In quantum mechanics, the eigenfunctions of a position operator are functions that represent possible positions of a particle. These functions are also known as position wave functions or position states. Of course, yeah, that kind of makes sense. So essentially what you're saying is that, okay, so if these are the eigenfunctions, right? So you're taking the eigenfunctions of the position operator. So these are all the possible position. So these are all the possible positions. So you're saying that the momentum thing is the same as integrating over all the possible positions times what? Times the wave function of position? That's what I'm not so. Why can you say that? But you're integrating over R, so you're integrating over. So you're taking. So essentially, you're doing a product of wave of functions, right? So you're multiplying the wave function of position by the position itself, by one possible position, and then you're doing these through all the possible positions that it has, and then you're integrating I'm struggling to understand the meaning of, like, you know, to understand why this makes sense. You're integrating. So this is basically, these eigenfunctions can be expressed. Yeah, so these are these things, right? In momentum spaces, the way some orthogonal functions, these orthogonal functions, Why do these eigenfunctions of the momentum operator? Okay, so the eigenfunctions of the eigenfunctions of this momentum operator, they have like a momentum component in it. Because we're defining the position. I mean, because the position and the momentum. Because in momentum space, the position is basically defined like this in momentum space. So essentially, we're saying that this is kind of the key. That's what we want to convert. We want to go from one space to another. We want to basically express one function using another as component. So we're just saying the eigenfunctions of this position operator essentially, we're saying if we take the wave function of position and we multiplied by we multiplied by each of the wave functions, each of the eigenfunctions of the position operator, how is that intuitively giving you? How is the integration of these intuitively, or the sum of these, even if you just think in the discrete case, how is the sum of these even intuitively giving you the wave function of momentum? I feel this is kind of one of the things I'm so fucking stuck with these that I just don't know. It's probably the 10th video that or 20th video that I'm doing about this, and I'm still stuck with that. The R and P operators are unitarily equivalent, with the unitary operator being given explicitly by the Fourier transform, namely a quarter cycle rotation in phase space. In physical language, P acting on momentum space wave functions is the same as R acting on position space wave functions. The whole thing with the Fourier transform helped to understand, like it just helped to understand. It just helped me to understand the thing that it's proportional to the frequency. That kind of justifies a bit why is it a Fourier transform. I'm just stuck with why you can even define it like this. We can write this function as a weighted sum of orthogonal basis functions. That's true. But why is then this coefficient the the wave function of momentum? And in this case, why is it a wave function of position? You take a basis that is basically the basis of the eigenfunctions of the position operator are all the possible positions that this wave function can take. Why is it obvious that if you integrate over these possible position functions times the wave function, that this gives you the momentum wave function, the possible momentums? Maybe because I don't understand sort of what are the semantics of these, or maybe I don't understand what the meaning of the product of the wave function of position times the eigenfunctions of position operator. So it contains the information. Yes, of course, the information, right? Like, I mean, it's what it's. These are sort of the coefficients in a way. It's just you're saying. If I have eigenfunctions if I have all the possible position elements and then I have whatever coefficient is in there, then this coefficient, it contains all the information about the position. So I can just call it the position wave function. I guess that's the rational, right? So you're saying it's a bit what's saying here. It's clear that if we specify this as the eigenfunction of momentum operator, then this element holds all the information necessary to reconstruct that. It holds all the information necessary, as in like it holds all the information necessary. Maybe that's it. It's just this is just because you peak the momentum. Basically, you peak the momentum eigenbasis. So essentially, these coefficients hold all the information. They hold all the information about the momentum of that particle. So you just add them up, and that's why you have an integral. I'm not crazy comfortable with the notation of these though, because here's like, yeah, these are coefficients. So this set of coefficients it's the sum of individual values. I guess this is just notation because it's the continuous case. So you have that wave function that has all the information, and then the eigenfunctions of these are basically. Why is this just also one element? So these are the eigenfunctions, which depend on k. It's a function of k, or it's a function of b as well, I guess. So that would be my, I guess that is maybe the next little piece of detail is how to understand how to calculate eigenfunctions of the position operator, right? So how calculate the eigenfunctions of the position operator. How do you calculate these things, right? What does GPT say? How can I calculate functions of the position operator? You will need to use the Schrödinger equation, which is the fundamental equation. Ah, do I? Oh, okay, yeah, so I mean, position operator eigenfunctions. Maybe that's what I need to understand next. How do these things come to us? So how do I find these things? But yeah, kind of. I think I got it. I think it's fine. I think I'm fine with these. It's basically what you're saying is, and then it just the way it turns out, because this this exponential thing pops up here as the eigenfunctions, right? This is just because that's the relationship between position and momentum, right? That relationship is defined by. It's still a bit shocking. It's still a bit shocking that you can do these. Well, of course you can do that in the classical case as well. You just do you don't need to have multiple. You don't need to have the data about the position. You just, if you have but that's what I mean. If you have an expression of position, but if you have a function over time, you can derive that, and then this derivation gives you the velocity. But that's not what you have. Typically, if you just have, because I always understand the wave function, right? If it's time independent, it's like the wave function is the equivalent as knowing a piece is equivalent to knowing a value of x, like a value of position. It's just that in this case you just have a probability of positions, the squared version of it. But it may be not exactly like these, right? So you have the wave function of position, and you can know the wave function of momentum, just because what you're saying is I can express position as a combination of any basis, right? Functions. And so that's, yeah, I don't know. I think I understand, but I'm feeling still a bit uncomfortable. As in, like, why is that even possible? I might ask Twitter. I think that's a good question for Twitter. Maybe there's just some, I feel there's some basic misunderstanding in terms of what the wave function is, as like the equivalent in classical stuff. Anyway, that was good. I think I feel like I've done a little step forward, at least.